All right, so we're talking about link layer bridges. So the idea here is to connect several LANs together with this link layer bridge. And just to emphasize what's going on here, let's assume that this host has a network layer where we are sending IP packets here. So there is an IP packet going down here. Then on this LAN, it will be encapsulated. This IP packet will be encapsulated into a frame where we have some header and a trailer, which is according to the standard which is on LAN 1. So the packet goes down here and goes up here and goes down here, and on this LAN it will be the same IP packet encapsulated now into a frame which is different. Okay? That frame would be the frame which is valid on this LAN. So in this case, it's an IEEE Ethernet frame here, and here it's an IEEE Wi-Fi frame. Okay. But it's the same IP packet here, and therefore the IP packet which is delivered up at the other end here is the same packet. So from the perspective of the network layer here, it doesn't see that there are different LANs here. Right. So that's the main idea. Okay, so we have MAC layer bridges that look something like this. And this is the common case when LANs are of the same type. So this LAN has the same as this LAN. So then this would be such a device where we could have an Ethernet on this side and an Ethernet on that side. So this is just an Ethernet MAC layer frame bridge. So it has no link layer in it, right? It just talks the same MAC layer, which is rather, it doesn't have an LLC layer in it. So it talks with the same MAC in both schemes. So this is the common case when the LANs are the same, and there is no need to change between frame formats. So how does this work? Let's talk a little bit about these transparent LAN bridges. Because what we want to do is to be able to connect together LANs without with the minimum amount of configuration. Everything should just work, plug and play. That would be good. So we would like to connect these LANs transparently, so stations that does not know or need to know about the existence of these bridges. So we have an actual topology that looks something like this. We have one LAN here, a couple of stations attached to it, and we have another LAN here with a couple of stations attached to this, and we have a bridge to them. Then the perceived topology for all these stations will be that we have a single LAN here. Right? So it's like connecting several LANs into a super LAN, if you like. So how does this work? Well, bridges is then responsible for moving traffic from one LAN to the other if it's needed. If it's not needed, it can just ignore that traffic. So a packet that goes from here to here just goes down here and it goes up and it goes like this, just as a regular LAN. But a packet that goes from here to here goes down in this LAN, but it's also switched over to the other LAN by the bridge. Okay? So the bridge needs to know something about what nodes are attached to this LAN and what nodes are attached to this LAN in order to sometimes let these packets go through. But if the packet does not need to go through, it will not switch it over to the other LAN, and that's a good thing, because the less traffic we have on a LAN, the better performance there is on that LAN. So there is no need to send out packets on LANs where there is not, the destination address is not there, right? So how do we do this? Well, the bridges inspect the addresses of all the frames it can pick up, and then determine whether the packet needs to be transmitted over to the other side or not. So if the source and destination address is on the same LAN, then the bridge does nothing with the packet it just received. If the source and destination is on a different LAN, then we basically switch it over to the other LAN. Okay. If the destination is unknown, then we also forward it over to the other LAN. Okay, because that's the safe thing to do. And to figure out when and when not to switch over these LANs, we need to learn these forwarding tables. So we use something called backwards learning to build this forwarding table. So remember, a forwarding table is on the it looks something like this. So this is the destination address of the frame on one of the incoming ports, and this is the output port. So we have some destination address here, and that is coupled to the corresponding output port. So in this switch, for instance, we have 5 output ports. So if there comes in a frame on one of these ports, it can be switched out to any of the other 4 or to none of them, right? And that is determined by this table. So the switch looks at the destination address of the frame that just came in and figures out, okay, in which port should it go out, if in any, right? And that is determined by the forwarding table. So the key now is to figure out, can we fill out this table without manual configuration? And yes, we can. All right, so let's see how that works. And the simplest way to do this is to do this through an example to figure out, to show the principle here. So here, in this case, we have 3 LANs. We have 1 LAN here, 1 here, and 1 here. We have 5 stations called S1, S2, S3, S4, and S5. So we can think of this S1 as being the network, the S1 here, we can think of that as being the MAC address for this computer, and S2 being this MAC address, okay? S3 this MAC address, and so forth. Okay, and in the beginning we have 2 bridges here which are connected to these LANs, and they know nothing. Okay, so maybe they've just been powered up, they have nothing in their forwarding tables. There is 1 forwarding table here and 1 here. They're completely blank at the moment. Okay, and these tables are then filled in by learning what's called backwards learning. So it works like this. Now, suppose that there is a frame going from S1 to S5. So S1 sends out a frame on its LAN with a destination address, which is S5, and a source address, which is S1. Okay, the frame comes from S1, it should be delivered to S5. Okay, so what happens then? Well, we put out the frame here, and in the frame there is a destination and source address. Right? That's part of the frame format. There is also a payload, which doesn't matter right now. It's only the addresses that we care about at the moment to fill out the forwarding table. So this table, this frame is then picked up by bridge number 1 that looks at these things, okay? It sees, okay, it is a frame that comes from S1, and it should go to S5. So what has this bridge learned? Well, the bridge has learned now that there is a node who has a MAC address S1, which comes into its port here. So you can set this, you can record this in its forwarding table. It says here, there is a node with MAC address S1, which is attached to port 1 of my bridge. This is what it learned. Okay? Then it looks at the destination address S5 and see, okay, do I have S5 in my addressing in my forwarding table? No, I don't. So then I send it out on all my ports. And in this case, there is only 1 port, namely port 2. And you shouldn't send it out on port 1 again, because that makes no sense. It just came from port 1, right? But it has a port 2, so it sends it out on LAN 2. Where it's picked up by bridge number 2. Okay, so what has bridge number 2 learned now? Well, it has learned that there is a node with MAC address S1 which is attached to its port 1. So it fills that into its forwarding table here. And then look at the destination address, it's S5. Where is S5? I have no idea. So I just send it out on all my ports. So I send it out on port 2, and then it makes its way to the destination address. Like this. Okay. So that's traffic number 1. And now what has changed now? Well, we have filled in 2 items in the forwarding tables for bridge 1 and bridge 2. Okay. So the bridges have learned a little bit of the topology yet, but not the whole topology. It just basically knows that B1, it knows that if I want to reach S1, I should send it out on port 1. Bridge 2 also learns that if I want to send something to S1, I should send it out in port 1. Okay, and then things will happen, hopefully, to get to S1. Any questions so far? Okay, we continue. Now, suppose S3 wants to send something to S2. So S3 here is in the middle. It should go to S2. So what happens? It sends out it forms a frame with source address and destination address. Transmits this out, and which is picked up by 2 bridges now, bridge 1 and bridge 2. And both bridge 1 and bridge 2 fill in a row in their forwarding table. So bridge 1 would say, okay, I have a node S3 which is found on my port P2. Bridge 1 would say, okay, I have a node S3 which is found on my port 1. Okay. It should go to S2. Do I know where S2 is? No, I have no idea. So I send it out on all my other ports, and it goes out on these things. So here we saw that the frame went from S3 through this up to on this LAN, where S3 is not here, but the bridge B1 didn't know this. So it took the safe thing, right? It just sent it out on this port. So this will be ignored on this LAN because there is no node with, sorry, it should go to S2 for sure. So it will be picked up by S2. But here, there is no S2, so this frame will be ignored on this one. Okay. But it has been delivered, right? Okay, it was sent out needlessly here, but that's okay, in the sense that it was not causing any error. It was wasteful, but it was not an error. Okay, next thing, S4 to S3. So it generates a frame. It's picked up by bridge number 2, which then fills in this row. S4 can be found on port 2. Looks at the destination address S3. And now there is a hit actually, right? S3 is found in the forwarding table. So it knows now, bridge number 2 knows that this frame needs to go out on this port. Okay. And it does that. It sends it out like this, and then it's picked up by S3. Here, bridge number 1 knows, okay, there is an S4 on my port 2, so I put that in here. And then look at, okay, the destination address is S3. What should I do with this? Well, I go into my table here and see S3, okay, it should be sent out on port 2. But it came from port 2. So therefore, I simply drop this packet, right? Because makes no sense to send it out here, because I know that the destination address is found at port 2. Okay? So it simply drops it. Okay. Then we go on, and if S2 needs to go to S1 here, it is picked up by B1. And now what has B1 learned? Well, it has learned that S2 is on port 1. It then looks at the destination address, which is S1. It finds it here. and it sees, okay, it should go out on port 1, but that's where it came from. So the bridge will simply drop this packet. Oops. Simply drop this packet, and then the packet is then delivered to S1 as it should be. Okay. So this is the way the bridges, by just listening to the traffic, can build up their forwarding tables, and depending on the state of the forwarding table and the destination address, it will either drop the packet or send it out on a single port or on all its other output ports. So in this case, the bridges only had 2 ports. But if you have 5 ports here, if you get in a frame with an unknown destination address, you send it out on all the 4 ports. If you get in a frame with a known destination address, you send it out on the appropriate port, one of the ports, not all of them. Okay. And then you learn and learn and learn, and you have the table inside this device, right? And it's completely transparent to the hosts. The host doesn't know about this. It doesn't know that the bridge exists. It just works. Okay. Any questions? Okay. So a few comments about this adaptive learning or backwards learning. So if we have a static network, tables are eventually filled up with all the addresses, assuming that all nodes, every now and then they send a packet. And then eventually the bridges which are connected to it, either directly or through another bridge, will learn about the existence of these nodes. And then therefore these forwarding tables will be complete and full, right? But the problem is, of course, that stations are added and moved all the time. They're powered down, then they're powered up, and they may be moving from one. If it's particularly if it's Wi-Fi, it goes from one place to another. So we need to be able to update these tables and forget about table entries also. So we introduced timers, on the average maybe minutes or so that to age each entry, each row in this, each row in the forwarding table have a timer associated with it. And if it hasn't heard anything from that host, which is has its address here, it will simply drop that row after a while, assuming that that host has powered down or moved away. Okay. So every now and then one throws this away, and if a frame arrives on the port which is different from what the forwarding table says, then the old row is then immediately deleted. Right? Okay. Then we also need to do something else, and that is to avoid loops. All right. So if we had I saw this, that, here's an incoming, here's a LAN, right? Now, suppose that LAN is also connected here. Then we have a trouble. I mean, you would have a computer attached to this one somehow here also. So here we have a computer whose frames can go in one port and then out in another port, in another port, out in another port. And that can keep on going forever if we're unlucky. So it's not so hard to draw topologies where we have frames which are running around inside the network, and according to the forwarding tables or the bridges, and this will cause something which is called a broadcast storm. So that frame will never disappear, and the whole whole network will fail. Okay. So, and the reason why we have this is that we have loops in our topology. So in this example, we have 4 LANs, 1 here, 2, 3, and 4, and we have a bunch of bridges. And these are connected, so bridge 1 and bridge 2 are connecting LAN 1 and LAN 2 with each other, and here there's clearly a loop here. And we also have a loop which goes from LAN 3 up here, down here, and so forth, like this loop. Okay. And there are, of course, many other loops here. Okay, now LAN 1 and LAN 2 here are connected with two bridges here. Why would we ever want to have it like this? We don't, okay? But I claim there are, it could be misconfiguration. Somebody plugged in the wrong cable in the wrong port or whatever. So that is one reason. But there is also a legitimate reason for having this. And why is that?
If one bridge fails.
Exactly. So if we have a bridge failure here, the other one can still connect these two things. So this is out of redundancy, for tolerance against failures. But anyways, there could be a misconfiguration or an intended configuration. But if we have these loops, then this backwards learning doesn't work. Okay, so then we need to do something about that. And what we can do is to remove these loops by logically disable some of these links. So if I go in and I say, okay, we're not going to use that link, for instance, then I've broken up this loop. Or I say, okay, we're not going to use this one, and then I've broken up another loop and so forth. So what we can do is try somehow to figure out which of these connections that we should disable, and then we can convert this topology into a tree, which is good, right? So the tree what we would like to have is to logically disable links such that the resulting topology is known as a spanning tree. So a spanning tree means that all nodes are connected. Spanning means that all nodes are connected, and tree means that one can find a root LAN or a node like this, and then we can find all others by just going down in this tree structure here. So tree structure is a special type of graph. Right. You know trees, perhaps. Right. Okay. But the key thing is that if we have tree, we don't have any loops. Okay. So can we do this? And we would like to do this without configuration. We would like to have a protocol that takes care of this for us. And that's what's this spanning tree protocol that we will talk a few minutes about at the end. But let's see how we can just form a tree from this topology in a structured way. So the spanning tree algorithm works as follows. We would like to find a bridge, which is the root. Okay, so we would like to find one bridge out of all bridges in our topology, which is the root on top of the tree, right? And we would like to do that in the following way. We basically say that the root bridge is the bridge which has the lowest ID. Okay, so we can think of this as having a MAC address, also this bridge, and that MAC address it is its ID. Okay, and since all MAC addresses are unique, if we have a bunch of bridges, one of them will have the lowest. Okay, and let's call that the root. Okay. And then for each bridge, except for the root bridge, we determine what's known as the root port. Okay. Okay. So suppose we have the root bridge is this one. Okay. And here we have another bridge. It has 5 ports, and one of these ports has the closest or least cost path to the root, and that is called the root port. So one out of these 5 will be the root port. Okay. So the root port is the port with the least cost path to the root bridge. And we will talk about how to state what the cost of a path is in a second. Okay. And then for each LAN, this is a LAN, right? For each LAN, we are attached then to maybe a couple of bridges, maybe this bridge and another bridge. We find the bridge and the port which has the best path to the root, and we call that designated port. Okay. So for each LAN, we select the designated bridge and its designated port, And the designated bridge is the bridge which has the least cost path from the LAN to the root bridge. And the designated port is the port that connects the LAN and the designated bridge. Okay, there are many definitions now, but we'll go through an example later on to clarify this. Right? Okay, but we find these. We find the root, and for each bridge we find the root port, and for each LAN we find the designated bridge and the designated port. Once we have done that, then all root ports and all designated ports are in active mode or forwarding mode. Okay, these are ports that can receive and forward frames. All other ports are put in blocking mode, so they are not active at the moment. They are not used for forwarding frames, but they're sort of in reserve. If one of the bridges will fail, then we recompute this spanning tree and we're back in business. Okay, so let's do an example here and see how this works. Okay, so we have our 4 LANs here, and then for each bridge we have an ID. So we have 1, 2, 3, 4, and 5. Okay, so simplified, we can think of 1, 2, 3, 4, 5 as the MAC addresses of these bridges. And each bridge has a port IDs. So bridge number 3 has 3 ports, 1, 2, 3. 1, 2, 3, sorry. Bridge 2 only have 2 ports and so forth. Okay, so we have bridge IDs and port IDs. Now, which one here would be the root bridge? B1, right. So here we have the root, okay, and that's because it has the smallest ID. Fine. Then, number 2 is to find the root port for each bridge. Okay, except for the root bridge, it doesn't need a root port. Okay, and here we would like to find the root port is the port which has the cheapest path to the root bridge. And we will compute the path cost as the number of LANs it needs to go over in order to reach the bridge. The number of LANs it needs to go over in the path to the root bridge. Okay, so let's here. So for B2, for instance, we have a path that goes from this port over this LAN to the root. We also have a path that goes from this port over this LAN to this root to the root. Okay, so we have a cost 1 path here and a cost 1 path here. So it's equal cost for these 2 ports, but we need to select one of those, and then we select the port with the lowest ID, which is 1 in this case. Okay, so then this becomes the root port of bridge number 2. Okay, then for bridge number 3, we see we have a cost 1 path that goes like this. We have a cost 2 path that goes like this, 1 LAN, 2 LANs. We have a cost 3 path that goes here, 1 LAN, 2 LANs, 3 LANs. Right? So in this case, it was pretty simple. We pick this as the root port. And we can continue to do this for all the bridges, right? So this is a B4's root bridge, and this is B5's root bridge. Okay. So now we have selected the root, and we have selected root ports for all the bridges except for the root bridge. Any questions so far? Okay. Then our next task is to select the designated bridge and port for each LAN. So now we look from the perspective of each of these LANs, which of them it needs to find 1 bridge and 1 port per LAN. Okay. And what we should select then is we should select the bridge which has the best path to the root. That's our designated bridge. And then there is a port on that bridge also, which is the designated port. Okay, so for LAN number 1, it's pretty simple. It can simply connect to the root directly through the root port here. So this is the designated port for LAN number 1. LAN number 2 then, which is the designated port for that one? It has 3 choices, this one, or that one. Least cost path to the root is this one, right? Okay, going here would be just wasteful. So no, for LAN 2, what is the designated bridge for LAN 2? Well, it's the root bridge, because that's, you want to reach the root bridge as quickly as possible. So it's going to be this one. Okay. Now let's see which one is the next. Okay, so next one is, B3 here. So it has now, LAN 3. So he needs to select a a designated bridge. So he has to choose between B4, B5, or B3. And he would like to pick the bridge which has the best path to the root bridge. Okay, so here we see we can go over B5, then we need to go this way up here. So that's not a very good path. It has cost 1, 2, 3. So this one is not here, but then you could select a B4 or B3, right? To go over B4, it needs to go over 1 LAN to reach the bridge. If it goes over B3, it needs to go over 1 LAN to reach the bridge. So which one should it choose? Well, then it chooses the one with the lowest root ID. Bridge ID. Okay, so B3 is the winner here, because it has the closest path to the root, and it has a lower ID on this one, which also has the same cost path to the root from LAN 3. Okay, and then we continue for LAN 4. It turns out that this is the designated port, and B3 is also the designated bridge for LAN 4. Okay, so now we're done. We put which are we going to enable here? So the root, okay, here we go. So all the ports which are either designated as roots are active, and all others are disconnected. So we will enable this one, this one, this one, but not this one. We enable this one, this one, this one, and this, but not this one, and this one, but not this one. Okay, so it's cleaned up like this. And now we have a loop-free topology. And to see this in clear, so here is a cleaned-up version of when we removed the ports and bridges which are not active at the moment. We can simply redraw it like this. So we put the root port up here, and we see that it's connected to a LAN here, and it's connected to a LAN here, and to another bridge, and a LAN like this, and a LAN like this. So now we clearly have a loop-free topology. Okay, so now when data needs to go from a LAN, say some data goes from LAN 3 to a host which is on LAN 2, the data goes like this. Okay, right. If after all the tables have been stabilized. Something that goes from LAN 3 that goes to LAN 4 would go this way. Something that goes from, say, LAN 2 to LAN 1 would go this way. And so forth, right? So now we have a loop-free topology, but maybe you can spot a problem with this topology.
Yeah, so we made transferring from LAN 2 to LAN 3 worse, right? By removing that link.
Yeah, so basically, if we go back here, so you say that going from LAN 2 to LAN 4, what you said?
LAN 2 and LAN 3.
Yeah, so exactly. So to go from LAN 2 to LAN 3, we actually had a nice bridge here, but now we force all this traffic to go this way instead. Yeah, so it's not optimal routes in this case. Yeah, but the routes that work, but they're not optimal, right? So that's one problem. There definitely could be better topologies, but this is one topology that works. So it's not the optimal thing to do. And also, if we see that if we have a lot of traffic that going from the left side to the right side of the route, everything goes through the route. So this could be overloaded also. So typically traffic becomes more and more intense the further up the tree we go, right? Okay. So in modern switched networks, one could also have other types of topologies also, not actually with loops in them. But then we also need to abandon the way we learned the forwarding table that presented here. But we will not cover them in this class, but if you go out in practice, you would see that, okay, when building LAN topologies, there are more advanced ways to do that than presented in this course. Okay. Now the other problem here is that, how can we don't want to configure this by hand as we did, so we want to have a protocol that takes care of this. And there is a protocol called the spanning tree protocol. So it was invented by Radia Perlman. I don't know which year, but fairly long time ago, when this problem of loops in the topologies were recognized. And I believe she was given a week to figure out the problem, right? So she was working, and the boss says, hey, fix this problem, you have 1 week. But she's a really smart person. I think she has a PhD in mathematics from MIT, which is a really nice school. So she figured this one out. And so this is an ingenious little bit of protocol work. First of all, she figured out, okay, we want to construct a spanning tree, and then devise the protocol to do this. So the spanning tree is found by bridges here, maintaining something called a bridge PDU, protocol data unit, which are transmitted to its neighbors. Okay, and so this bridge PDU is the best guess of the bridge on which bridge is the root. So the bridge PDU has the transmitting bridge ID. Okay, so this one has its own ID. The ID of the bridge that it thinks is the root, and the cost it takes to reach that bridge. Okay, number of LANs it needs to go through, perhaps. Okay, the cost of this to reach the root bridge is the sum of all the LAN costs on the path to the root bridge. Okay, and the LAN cost typically decreases with the LAN data rate. So we could have so suppose we have a 10 megabit, 100 megabit, and a 1000 megabit. So this is the data rate over the LAN. Then it's more costly to transmit over a low capacity LAN than over a high capacity LAN. So I don't know, I just invent some cost here. So maybe if this is cost 1, then this is maybe cost 2 and this is cost 3, or maybe it's 10 and 100 or something like this. Okay. So it's cheaper to transmit the frame over a high capacity LAN, right? It takes less of that capacity of that LAN. Right? So that's the rationale behind this. But for simplicity now, let's just think of each LAN having the same data rate. So then the cost of going a LAN is the same. One LAN costs 1, 2 LANs cost 2, 3 LANs cost 3, and so forth. Okay. So each of the bridges then stores the best bridge PDU has seen so far. Okay, so how do we compare bridge PDU? So comparing this PDU, X1, R1, C1 with X2, R2, C2 is done hierarchically here. So first we compare the following. So we select the bridge PDU with the lowest root ID. Okay, which means that we compare R1 with R2, and the best one is which one that has the lowest ID. Remember that the root bridge is the bridge with the lowest ID. Okay, so we compare R1 and R2. If this R1 and R2 happens to be the same, then we go to the next level of comparison, and that is to select the bridge PDU with the smallest path cost to the root. So second is that we compare C1 with C2. Okay, and then we select the one which has the lowest cost. Okay. Then if C1 is equal to C2, we go to the third tiebreaker, and that is we select the PDU with the smallest ID. So then we compare X1 and X2 with each other. Okay, so that's how we compare PDUs. And now we're ready to run the algorithm. So initially, each bridge on power up, so what does the bridge know? It knows essentially nothing, right? It knows its own ID. Okay? And in a strike of feeling superior, it will say, I'm the bridge, right? Okay, so that's the initial thought of all the bridges. And therefore, its initial PDU would be X. Okay, bridge X would, I'm X, the root is X, that is myself, and the cost to reach myself is 0. Okay, so this is the initial setup for all the bridges, okay? The sender is X, the root is X, the cost to reach the root is 0. Then we transmit this PDU out on all these ports, okay? So send this out the port, and then there is another bridge somewhere else picking this up, okay? Then we have two bridges. Both of them think they are the root, but only one can be the root, right? There's only one, the one with the lowest ID. So essentially, just compare the PDU you got with the PDU you have stored, and you select the best one. Okay? So, if a PDU is received on a port, what do? First of all, we add the cost of for the LAN from which it came from. Okay, so if the received one is SRC, then we update it to be SRC plus 1. Okay, then we compare the updated PDU with the stored one. If better, then we adopt the one that we have received, because this is better than what we have. Okay, and then we set the port from which we received this better PDU as the root port. Okay, because now if I get a PDU from this port, which is better than I have stored, I know that the bridge on the other side has a better path to the bridge than I do. So therefore, this should be the root port, and I should update my PDU with my new knowledge. Namely that I can reach the port, the root, by going out of this port, which adds the cost 1 to my path. Okay. But that's how I know, that's my knowledge at the moment. Okay. And if we think about that, eventually, only the designated, okay, so what do? We save the new bridge PDU, we set Y as the root port, and we stop transmitting the stored protocol data unit on that port, because that makes no sense now, because I know that there is a better PDU on that LAN. And if we think about that, eventually only the designated bridge will transmit bridge PDUs on its LAN. And therefore we are done. Each PDU will be like the sender, the root, and the cost, right? So if we think about it, after we are transmitting all these PDUs to each other, we will converge at the same root ID. Okay? Different bridges will of course have different addresses, right? And different costs to the root. But this one will be the same for all bridges in the network. And then it also knows it knows its root port, so it knows where to send data to. And also it knows its designated port. It knows if it has a designated port. And how do I know if I have a designated port or not? Well, it's because if I transmit my PDU on a port, then that is the designated port for that LAN. Okay. Remember, I stopped to transmit this on the root port. But the bridge which is connected to a LAN, which has the best path to the root, will still keep on transmitting its PDUs because it has the best bridge PDU on that LAN. Okay. So if you go back and look at this a little bit, you would see that this is indeed the case. To summarize, we have talked today about how to connect LANs with switches, and we have talked about when we use transparent bridges, which learns the forwarding tables without the interaction of the hosts and configuration. We also learned that if we have loops in this topology, we need to do something about it. And then we build a logical topology, which is a tree. And that tree can actually be formed by executing a protocol which is distributed. So we don't need to configure the tree. And of course, since every configuration is subject to change, I just changed the topology now, then everything needs to have a timer. So at some point you repeat the process, right? And then the network is self-healing from that perspective. Okay. But that's it for today, and I think next time we will talk a little bit about Wi-Fi, if I remember correctly. So see you then.